Also discuss the implementation of 8-point Radix-2 FFT structure, and we also solved a numerical example for 8-point Radix-2 FFT. And then we concluded the last lecture on a bit reversal technique, which is used to perform data shuffling without performing stage-by-stage decimation in time. Now in this lecture, we will perform computational analysis of n-point Radix-2 FFT. As we already know, FFT is just an efficient way to calculate discrete Fourier transform. So in order to find how many times Radix-2 FFT will be efficient or faster than the conventional DFT, we must have the knowledge of the required computations of Radix-2 FFT, which means that when we will implement n-point Radix-2 FFT on our computer, how many operations will be performed by our computer in order to provide the required result of the n-point DFT output. So the basic objective of this lecture is that we have to find how many multiplication and additions will be performed by our computer for n-point Radix-2 FFT. And this is the Radix-2 FFT structure, which is also called a butterfly structure or a crisscross structure. And the basic building block of this FFT structure is a single butterfly operation, which is represented by a single cross structure. So this is a single butterfly operation, this is another butterfly operation, this is the third butterfly operation, and so on. Now in every butterfly operation you will find two total factors. In this butterfly operation, the first total factor is W20, which is on this diagonal line, while the second total factor is W21, which is on this straight line. Similarly, in this butterfly operation, which is represented by purple color, you will find the first total factor W41, which is on the diagonal line, while the second total factor of this butterfly operation is W43, which is on this straight line. Similarly, as you can see, this blue color butterfly operation also contains two total factors. The first total factor W40 is on the diagonal line, while the second total factor W42 is on the straight line of this butterfly operation. Similarly, let's take an example of this green color butterfly operation. This green color butterfly operation also contains two total factors. The first total factor is W82, which is on the diagonal line of this butterfly, while the second total factor W86 is on the straight line of this butterfly operation. So the conclusion is, in every butterfly operation we will have two total factors. One total factor will be on the diagonal line, while the second total factor will be on the straight line. Now, the approach which we are going to use in this lecture for finding the required number of computations is that firstly we will try to find the required number of computations for a single butterfly operation, so that we can calculate the required number of computations for the whole structure very easily. So let's see how we can do it. The total factors which are presented in the Radix-2 FFT structure have these values, and the calculation of these values has already been discussed in previous lecture. And these are the Radix-2 FFT equations which we had discussed in detail in the previous lectures. Here I have presented these equations again just for your reference purpose. So equation 1 is used to calculate the first n/2 samples of the n-point DFT output, and equation 2 provides the remaining n/2 samples of the n-point DFT output. And equation 2 can also be used alternately as equation 3, where we can replace Wn(k) plus n/2 total factors by simply minus times Wn(k) by using the symmetry property. And in all these equations, the value of k can vary from 0 to n/2 minus 1, because here we are combining n/2 point DFTs. So a of k represents the first n/2 point DFT, while b of k represents the second n/2 point DFT. Now, in order to understand these equations in terms of the butterfly operation, let's assume some values. Suppose n is equal to 8, which is the case of 8-point FFT, and put k is equal to 0 in equation 1 and 2. So when you will put n is equal to 8 and k is equal to 0 in equation 1 and 2, so equation 1 will become this equation, which is capital X of 0 is equal to a of 0 plus W80 times b of 0. Similarly, this equation 2 will become x of 4 equal to a of 0 plus W84 times b of 0. Now, just focus on these two equations. In these equations, we are using a of 0 and b of 0. And what is a of 0 and b of 0? A of 0, as I just mentioned earlier, a of k represents the first n by 2 point DFT and b of k represents the second n by 2 point DFT. And if the value of n is equal to 8, then n by 2 point DFT means it is a case of 4 point DFT. So a of 0 represents the first sample of the first 4 point DFT, while b of 0 represents the first sample of the second 4 point DFT. So as we can see, a of 0 is contributing in the calculation of two frequency components, which are x of 0 and x of 4. Similarly, b of 0 is also contributing in the calculation of same frequency components, x of 0 and x of 4, which means that every single 4 point DFT output will contribute in the calculation of two frequency domain components of the 8 point DFT output. This is how we can make 8 point DFT output with the help of 4 point DFT outputs. Each 4 point DFT output has to contribute in the calculation of two frequency components of the 8 point DFT output. Now, if you understand these equations in terms of butterfly operation, then you will find these two equations are making a single butterfly operation because it is taking two samples at its input, which are a of 0 and b of 0, and they are providing two frequency domain sample values, x of 0 and x of 4. So a of 0 will remain as it is during this calculation, while b of 0 will be multiplied with two total factors, W80 and W84. So in a single butterfly operation, we will have two input samples, a of 0 and b of 0. There will be two total factors, which are W80 and W84. And similarly, the output of a 2-point butterfly structure will also be two samples, which will be x of 0 and x of 4. Now let's come to another case where we are substituting k is equal to 1 and n is equal to 8 in these two equations. When we will put n is equal to 8 and k is equal to 1 in equation 1 and 2, we will get these results. X of 1 will be equal to a of 1 plus W81 times b of 1. Similarly, x of 5 will be equal to a of 1 plus W85 times b of 1. Again, here you can see a of 1 and b of 1 both are contributing in the calculation of x of 1 and x of 5. So basically, this is again another butterfly operation where we are taking two input samples, a of 1 and b of 1. And by multiplying b of 1 sample with two different total factors, W81 and W85, we are getting two frequency domain outputs, which are x of 1 and x of 5. And you can also verify these total factors in the butterfly diagram. You will find that in a butterfly operation where W80 is present on the diagonal line, then in the same butterfly operation you will find the other total factor will be W84, which will be on the straight line. Similarly, in the butterfly structure where you will find W81, then the second total factor will be W85. W81 will be on the diagonal line and W85 will be on the straight line. So you can verify this thing through a butterfly structure. And the important thing about butterfly operation which you should remember is that in every butterfly operation there will be two total factors, Wnk and Wnk plus n by 2, as we have discussed here by taking an example of n is equal to 8 and k is equal to 0 and 1. So Wnk total factor will be on the diagonal line while Wn k plus n by 2 total factor will be on the straight line.